Welcome to the Stutzman channel, and my name is Terry. In this video we're going to be talking about RL circuits, and if you're an automotive technician you may find this helpful. You can use some information here, like if you're current ramping an injector, solenoid, primary on a coil for ignition coil. And so let's see where it's all going to take us here. Now I have a circuit up here. I have a 12-volt battery, I have a switch up here, I have a resistor, and I have an inductor. Now, as you can see, I have a dash box around here where it shows that the resistance is kind of enclosed with the inductor. Now, this being an RL circuit, R being resistance, L is the inductance measured in henries. But what I'm trying to show here is that the resistance of the windings of the coil is enclosed with the inductor. Now, how did he draw that? Electrically, it's the same thing. This is how it would look electrically to the source voltage. You have your resistance of the windings, and then you'd have your inductance. Okay? Now, when you put your amp clamp around this here wire for this here circuit to look at this current ramping, you've probably seen this here type of curve here. Well, and have you ever noticed that some of the curves, you know, they're kind of like leaning like this, and then in another inductor you might see it a little bit straighter up, and then sometimes it might be even further down. Well, there's only two things that causes the slope of this here exponential curve to change, and that's the inductance and that is the resistance. These two components right here. Now keep in mind that this here resistor, I have it shown as for the windings of the inductor, but it can also be an external resistor. You know, I could put another resistor up here, and then I would just add up to two resistances. But in this case, we're just going to use that one resistor. Now, let's talk about this here curve. Now this curve is called an exponential curve, right? And and this is the current. And the question is, well, why does this curve happen? You know, if you had a resistor and you looked at the current, you know, it would go along and it would just go straight up. But here we can see that this here is curved. The inductor's purpose is to oppose any change in current. If there's no current, like when the switch is open and you start throw the switch and ask current, inductor says, I don't like it. I'm going to do everything I can to hold back on this current. And you're seeing that effect through this here curve. Now the way it's doing that is what's called a back EMF that's induced across the coil. Now, soon as you close the switch at time equals 0, at that very instant, what has happened? How much current do you think is going in this circuit once I close that switch? I close this switch up here at time equals 0. Soon as that happens, the current is 0. Now, how much voltage is across that resistor? Right? 0. Well, there's no current. There's not going to be any voltage, right? So we got 0 volts. We got 0 amps. Now look, we had 12 volts across the battery, so that 12 volts has got to be somewhere. Well, it is right across the inductor. The whole supply of volts is right across there. Now we got 12 volts here. Now, when it induces the voltage across itself, the coil, we're going to have the polarity of plus and minus as shown here. This plus is over here with this plus. Now, these two voltages together, 12 and a 12, if you subtract the difference, what do you got? 0 volts. 0 volts, no current. So that's why we don't have any current at that very instant. At that very instant, the current is max. It is coming in, and the inductor is doing its most at that point right then. At this point right here where the current is 0, that is where it is opposing the change in current the most throughout this whole entire graph of this exponential curve. You can think of this here voltage as it's an opposing voltage. Take batteries for example. If I had two batteries, let's say I had a battery, and then I had another battery, and they're in parallel, and plus, and I subtract the difference between them, I'm going to get 0 volts. right? If I measure between them, I got 0 volts. That's exactly the same thing that's happened here with this inductor. Think of this here as a battery, and now this battery will be up in here. This will be plus, this will be minus. Now this voltage here that's across the inductor is opposing the source voltage. That's why we don't have any current, okay? At that very instant. But now, let's take a look at the voltage that's across that inductor. This is the current. So here's our time. Here's the voltage that's across the inductor, okay? Well, we just said at that very instant, let's look at this as time is 0. Right up here, let's say that's 12 volts. Right there. There it is. Sitting up there. Now, as this current is coming up, that means that the voltage across the inductor is going down. So it's going to be coming down. And as this is going down, the current is going up. But this voltage here, as you can see, it is working with the source voltage, and then it is opposing that voltage, that source voltage, okay? That's why we have this curve. And then it just comes on down, and then by the time it gets down to here, well, there isn't any voltage across the inductor itself, okay? So now, that means that when we're up at this here condition, we call that steady state. The inductor has done all it could to oppose that voltage, that change in voltage. When we get up to this point here, we're at maximum current. The inductor is not opposing anymore, and at that point, it is not even an inductor. It is nothing no more than a piece of wire that has a resistance. So the inductance is pretty much out of the circuit. It's not opposing anything as far as the current. And at that point, when it's up here, then we have 0 volts across that inductor, okay? So you can see that as this voltage is coming down, let's say right here it was 5 volts. Now I've got 5 volts and I got my 12 volts for my source voltage. I subtract, I got 7 volts net. And so that's pretty much what's in the circuit to try to drive this current. But as you can see, as the current goes up, the voltage across the inductor goes down. That voltage, in conjunction with the source voltage, is the actual voltage is what, the net voltage is what's creating the current. And so therefore, you're going to see this exponential curve. Now, this part in here where you see it curving, the ramp itself, that's called the transient response because the current is changing during this time, okay? And like I said, when we get up here to the very top, and now the current is maxed out, there's no more inductance. The only thing that's limiting the current now is the windings resistance, okay? Just the R. And at that point, we call that the steady state, all right? Steady state condition when it hits the max. Now, sometimes you hear some people say it's saturated. It's going up and now it's saturated. Well, that's not a correct term because saturation pertaining to magnetic fields, I'll give you an example. Make it a little easier to understand. Let's say I take an electromagnet and I put some current through it and I got so much of a magnetic field and I can measure it and I got the strength of it. Now, I turn up my voltage, my current goes up, oh, my magnetic field got stronger. Okay, so now let's say I just crank that voltage right on up and now my current goes up. Now my magnetic field goes up. Well, I'm going to reach a point where I can keep turning this voltage up and that current, even though the current is going up, 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 my magnetic field is going to hit a plateau where it's not going to get any stronger. At that point, that's where we say it's saturated, okay? So that's why we want to say steady state, okay? Now, and when we hit this steady state, as I already mentioned, the only thing there is going to be the voltage divided by the, this here, in other words, this here current for a max current is going to be equal to I is equal to voltage divided by the resistance. It's the only thing. Now the inductor, like I said, it's out of the circuit. Now just to complete this over here on this side for the steady state. Steady state, we're up here at the top, right? And let me just write up here steady state. Our steady state is going to be V divided by R. So our V is 12, our R is 10, so our current is going to be 1.2 amps. Okay? Now, what's the voltage across the resistor? Well, we got 10 ohms. Voltage is equal current times resistance. 1.2 times 10, 12 volts. Now, if I got 12 volts across the resistor, what do I have across the inductor? 0 volts. All just what we just talked about. Now, there's a thing about when coils are charging up, it takes a certain amount of time. Have you ever noticed, like when I just said how these curves, you know, they kind of look like the ramp is leaning, you know, you have a different slope depending on what inductor you're looking at. Well, believe it or not, it takes a certain amount of time for the coil to charge up. And we can calculate and figure that out, and that's called a time constant, right? Now, a time constant is the amount of time it takes for a coil or inductor to charge to 63.2% of its max value. That's that value over here that we just talked about, in this case 1.2 amps. If I take 63.2% of that, 1.2, the time that it takes for that to happen, that is called a time constant. Now the time constant is figured out by using this here equation. We use this here Greek letter tau to represent time in seconds. That'll be our time constant. And that's going to be equal to L, which is inductance, measured in henries, divided by the resistance. All right, so let's look at our example here. We have our inductance is 1 Henry. Our resistance is 10 ohms. We divide 1 by 10, we get 0.1 seconds, okay? 0.1 seconds, all right? Now, as I mentioned, it takes 0.1 seconds with this coil and this resistor for it to reach 63.2% of its current, all right? So let's look at this down on the timeline. Let's say right here, right there at 0, we're going to start right there. Now we're going to go over 0.1 seconds. 0.1 seconds. Now that is called tau, or one time constant. And then I could come over 0.2 seconds. I can double that and I can say times 2, and I will get 0.2 seconds, and that would be 2 tau. And across we go, right? 0.3 seconds, 3 tau, 4 tau, 5 tau. And by the way, when I hit 5 time constants, and that's 0.5, 5 times this 0.1, that will be 0.5 seconds. That will be the amount of time it takes for this here coil to fully charge up to reach the steady state value. And so, you know, that can come in handy. Now there's an equation that describes this here exponential curve. And with that equation, we can calculate anywhere on time of what our current will be. All right, let's use an example. Let's say we're running along here 0. I close the switch. 0.25 seconds later, let's call it, oh, I don't know, somewhere in here, wherever that turns out to be. I want to know what is the current going to be, you know? What is the current going to be at 0.25 seconds later? Now, the equation that describes this here curve, for us to allow to do that, is going to be I, a function of time. The only thing that means here is that the current is changing over time. As you can see, it's changing. And that's going to be equal to our max current. Remember, that is V divided by R. And then we're going to multiply that times 1 minus E minus T for time divided by tau. Now E is a base for a natural logarithm, and it's too much to cover in this here video, as it would just get too long. So just look up Euler's constant if you want to know a little bit more about it. The value is about 2.718 approximately. It's an irrational number, just kind of like pi. You know, it just goes on and on forever. Now, a time that we're interested in is 0.25 seconds. So let's just go ahead and we'll put that in. And then we want to know what max current is, so that's 12 divided by 10, which we know that's going to be 1.2 amps. And then we're going to say 1 minus E. A T up here is going to be a time that we're interested in, which is minus 0.25 seconds divided by tau. And as you remember, tau was equal to L divided by R. And then that was 1 Henry divided by 10 ohms, which is equal to 1/10 of a second. So then we'll put that down in here, okay? And then we will work that out. And I think I've already got it here. Let me see. Yep, and I've got 1.1 amps, okay? So I'm gonna just bring it right on down in here. So that is 1.1 amps. And that's what the current would be 1/4 second after we close this here circuit, okay? Now, we talked about this here time constant of 0.1 seconds, and we said that after 5 time constants, it would be fully charged, so that would be 0.5 seconds. So anywhere we want to know what the current is, we can figure it out, okay? Josie, be quiet. Thank you. Now you might be wondering too about, well, what about the voltage? Can you calculate the voltage anywhere during time across the inductor? Because you know it's coming down as the current is going up. Well, yes, we can. What we can do on that is we got another equation. And then that one is following an exponential curve also. But it's a little bit more simpler. So we can say that the voltage across the inductor, function of time, all we have to do is, what is our supply volts? That's it, 12 volts, right? And now we multiply this 12 volts, E minus T divided by tau, and there we go. So all we have to do is plug in a time to, you know, how much voltage is across the inductor, and we can do it. So I'm gonna leave that one up to you guys because we're already getting a little bit late in the video here. So look, what we're going to do now, let's go over to the software, and we're going to look at PicoScope, and we're going to look at this here injector, a fuel injector. We're going to make some measurements, and then we're going to come back, and then we're going to see what we can extrapolate from it, and based on what we did here. All right, let's take a look at a fuel injector current ramp, and we're going to go over this here current ramp like we had already discussed and getting some measurements off of it. Okay, I'm looking at this here current ramp. This is of an injector number 5, I believe it is. Yep, and it's off a 2000 Buick LeSabre. So I took this capture a few years ago during the winter time. So let's see what we got. I'm just going to use this one right here, the second one. Okay. Now the first thing we want to know is what is the maximum current that this injector has. So let's get that measurement, and I'm going to call it 1.109. So I'm writing these measurements down as we go. So you may want to do the same thing if you want to follow along. Now I'm going to come across, and I'm going to go ahead and I'm going to bring a cursor over here and start our time at 0. I need to pull it over just a little bit more. Okay. Now, this up here, this is our maximum current. If you remember, one time constant would be 63.2% of the maximum current. So to find that, I'm going to bring a calculator up. We're going to take 1.109 and we're going to multiply it times 63.2%. That is going to give us I'm going to call it 0.7 amps. I'm going to come up into here and I'm going to type in 0.700 amps. Now there is our 63.2% of our current right there. Now I'm going to pull another cursor out and I'm going to line it up right at that point right here. So I need to come over a little bit, and that's where we need to be. Now here, the time from here on this first cursor on time to this second cursor for time is going to be representing our time constant for this here fuel injector current. Now if we look up there, we can see that we have 935 microseconds is the time between these two cursors. Now another thing that I like to get is what is the resistance of this here inductor. So we have a voltage up here. Here's the voltage that's for the inductor. This is measured across the control side of the inductor. And let's just pull the cursor down and let's just see what our voltage is. Now for that I got 14.75 volts. Like I said, it's a little high, but this was taken during the winter time when it was cold, so probably that's not unusual for the voltage to be a little high. Now another thing to note is that let's look at the time constant here. This is one time constant. And if you remember, I said that it takes 5 time constants for the coil to be fully charged. So let's lock the cursors. And I'm just going to move this over to here. So this is one time constant. There's 2. And there's 3. And you can see that I have a little bit left over. So it's not 5 time constants, but you can see that it is charged a little past 3, which in effect, that would give us what percentage of the coil that's charged. And that's 95%. And so if it was 3 time constants, it would be 95%, a little bit more. So, you know, it could probably be around probably 97%. And we can actually calculate and figure that out. In fact, let's go ahead and do that. Let's bring this back. Let's get this line back up on 0. That looks pretty good. And let's take this one right here and let's bring him up. Whoop, let me go back and unlock the cursors. Sorry about that. Okay, that looks good. Let's unlock the cursors. And let's take this one and slide him over. And we'll just see what the max current for that would be. Yeah, let's just put them right there. Now if you can look right up here, you can see the time between here, these two time cursors is going to be 2.988, but we'll just say that it's going to be 3 milliseconds. And so we'll make a notation of that time also. Now let's go to the board and let's see what we can figure out from all of this. All right, we're back. Now I redrew the circuit here. This for a fuel injector. Remember, this is R for our resistance, and we have an L for inductance, but we don't know what that is, do we? Let's see if we can figure out what it is from our calculations we made. Now, typically, you know, a fuel injector is switched on the ground side. I'll show it over here on the positive side, but just to be to conform what we did earlier, I'm just going to keep the switch in the positive side. It does not make any difference, okay? We had a switch down here, be the same thing as far as in the results of our calculations. Now, we had our waveform, okay? Now I'm just putting on my notes here that I got. We knew that our max current here was 1.109 amps, okay? Steady state condition. Now we knew also that from here we put a cursor and we came down, right? And we snapped a line. And we knew that this was 63.2%. And I'll put that over here. 63.2% of our maximum current, and we saw that that was 0.7 amps. Okay, you with me so far? Now we look down here for our time cursor. We saw that we had 935 microseconds. So this down here, 935 microseconds. Okay. All right. Let's do, we need to do our time constant, don't we? All right, so our time constant is tau equals L divided by R. All right. Do you see a problem? Well, I don't know what R is, and I don't know what L is. So, but do you remember we looked up at our supply volts, and we saw that it was 14.75 volts, right? So let's step over here to the side, and we're going to see that V is equal to I times R, right? Now, we want to find what? Well, we need resistance. We want to know what is the resistance of the windings on that fuel injector. Now, for the ones that don't know how to transpose equations, I want to solve for R. So what does that mean? It means I need to get R by itself, and I want to get rid of I. So what do I need to do? If I take, right? If I take and divide both sides of the equation by I, remember, whatever I do to one side of the equation, I have to do to the other side. It is still equal. Whatever I do, if I do it to both sides, it's still equal. Now look at here. I divided into I, they cancel out. I and I gives you 1. 1 times R is R. So now I'm left with V divided by I is equal to R. Okay, you remember that voltage? That was 14.75 volts. Well, what was my current? What was my max current? Well, we already knew that. That was 1.109. So now I got 1.109 ohms. Okay, so let's see. Work that out. I've got 13.3 ohms. That is our fuel injector winding resistance. Okay, let's make a note of that. Fuel injector winding resistance. Okay? All right. Now let's go back up to our time constant equation. So now tau is equal to, what is our inductor? Well, good gosh, it keeps going on. Now we need to know our inductance. Okay. Well, let's see what we can figure out on that. All right. We want to calculate inductance. How many henries is this fuel injector got? I want to solve for L. Now, if I multiply both sides of the equation by R, right? Cancel, cancel, leaves me with L. Multiply this side by R. Now I have my time constant times my resistance, and that is going to give me my inductance. So what is my time constant? Well, here's my time constant right here. So I can write down 935 times 10 to the minus 6 seconds times R, which is 13.3 ohms, and that is going to be equal to, and I've got 12.44 millihenries. Okay? See, this is pretty easy stuff, right? Easy. All right. Now, let's see what else that we got. So, if this here is our time constant, how long is it going to take for the coil to be fully charged? 5 time constants. So, here's our time constant. So, if we say 5 time constants, and that's going to be equal to, let me just write it down here, 5 times 935 times 10 to the minus 6 seconds, and that is going to be equal to, and what did I come up with here? Save us a little bit of time here. I got 4.675 milliseconds. That's how long it's going to take for this here coil to get fully charged. 5 time constants. Okay? All right, what else have we got here? Oh yes, we wanted to know after 3 milliseconds how much current is in that coil. Now we could have took the cursor and just dropped it down and looked at it, but you know it's kind of cross flat. You know it's hard to tell because it gets smaller and smaller and smaller as the current gets up there, right? So we don't really know. So we're going to look at that. So let me get, let's see, let's erase this part out. All right. Now, do you remember the equation of where if whatever time we want, and we want to know what the current is, we use the equation that we had a little bit earlier in the video, and that was I, function of time, is equal to V divided by R, that is our max current, times 1 minus E minus T divided by tau, and that is going to give us what the current is at 3 milliseconds. In other words, we found from here to here was 3 milliseconds. Well, at that point right up there, how much current do we have 3 milliseconds later after this here coil has been turned on? All right, so we're going to say when it's 3 milliseconds, and we're going to say V divided by R, so we got, we said that was 14.75 volts divided by R, which is 13.3 ohms, times 1 minus E minus T for time, which is 3 milliseconds divided by tau, and our tau was our tau is 935 milliseconds. Yeah, we measured that. Microseconds, I'm sorry. Now, if we multiply this out, then we will find that at 3 milliseconds, we will find that our current is going to be equal to, I got 1.0642 amps. Now remember, there's our max current, 1.109, and 3 milliseconds later, we got 1.0642 amps. So what percentage did we almost get to it? So if we take 1.0642, divide that by 1.109, then we will see that we will get, and I came up with 96%. So we got pretty close. And just as a final one, something extra, and we want to look at the voltage across that inductor, just so we can look at that. I got a little example here. Let's say we want to know the voltage across the inductor. And we are looking at, at one time constant. At one time constant, 935 microseconds later, what is the voltage across that inductor? And mind you, we can figure it out anywhere along there, but I'll just pick that one out, okay? So let's say we're going to be looking at our battery voltage. What is our battery volts? 14.75. And let me just write it out. Voltage, say battery, and then I do our equation, which is E minus T divided by tau. And then we come back to voltage across the inductor when it is at one time constant. and that is going to be 14.75 times E. Now minus our time is going to be 935 microseconds. 935 microseconds divided by tau, which is 935 microseconds. And then we can see that that is going to be, now you can see this is going to be e to the minus 1. That's okay. And then that's times 14.75. And so you can see that this here minus 1, that's going to be 60. That value right there is going to be 0.632. Okay? And you take that times 14.75, and when you do that, you're going to see that that is going to be 5.42 volts. And that's the voltage across the inductor after one time constant. Okay, that's going to wrap the video up here. So let's recap what we learned in this video. First of all, we learned that most people, mind you, I said most, I didn't say all. Most people don't care how things work. The only thing they really care about is when they break. Then that's when we start worrying. And then the next concern is, well, who's going to work on it to fix it? And the biggest thing, biggest concern is how much is it going to cost? You know, so I realize this video is not for a lot of people. You know, I find it interesting, you know, but if you do, you know, let me know what you think. I look at it that all the information that you can get, you know what? It can help you. You never know how it can help you down the road. The more you understand how something works, you can take that information and you can apply it in your troubleshooting, diagnosing. You can develop your own strategy how to diagnose something because you know how it works. You know how to check it. But if you don't know how it works, then you ain't going to have a clue on how to get something back together to work that you don't even know how it works, right? Makes sense? So anyway, just a little rambling, I guess, but you guys take care. If you got any questions, comments, concerns, you know, let me know. And we'll see you guys in the next video.